Hey guys, and welcome back to this class, Bayesian Machine Learning in Python, Part 1. In this lecture, I'm going to go over a great practice opportunity to really allow you to solidify what you've learned in this course. To recap, we went over some classical frequentist A/B testing methods and discussed some problems they have, like imprecise confidence intervals and the misinterpretation of p-values. Specifically, we focused on data that was Bernoulli distributed, because it's highly applicable to online businesses and digital media. It covers things like click-through rates, conversion rates, and so on. Later, we looked at a few adaptive methods that allow you to simultaneously test multiple different versions of something, while at the same time adapting and updating your beliefs about which is best based on data. We looked at the mathematical properties of each method to show that while they all work in the sense that they allow you to both explore and exploit, they all use a different strategy. In the real world, we're not so much interested in the mathematical properties of each method, like how they converge asymptotically, but rather we want to know which performs best empirically. You saw that we can generate synthetic data and run an algorithm on that data. You'll notice we didn't write any code for epsilon greedy and UCB1, but hopefully those were pretty straightforward since they were only a few lines of pseudocode. To really get a feel for how all these algorithms work and how they compare to each other, it would be a good idea to do your own simulation, implement all these three algorithms, and tally up the reward that they each end up with. Some characteristics you might want to look at are: which was the easiest to implement, or were they all relatively the same? Which converged to the best bandit the fastest? And what is the total loss compared to what you would have gotten if you had already knew which the best bandit was and played only that bandit every time? Hey guys, and welcome back to this class, Bayesian Machine Learning in Python, Part 1. In this lecture, we're going to do an even more complex example of conjugate priors. Sometimes the thing we're measuring isn't a coin toss or a category, but instead a real number. Of course, Gaussians are a common distribution for modeling real numbers, so in this lecture we are going to use the Gaussian as our likelihood. One fact you might recognize right away that makes this more complicated is that while the Bernoulli and Dirichlet likelihood only had one parameter, the Gaussian has two. It has both mean and variance. Since we want to move in small steps, this lecture is only going to place a prior on the mean and assume the variance is fixed. Later we'll discuss some follow-up exercises you can do once you understand this one. So to start, we are going to be using precision instead of variance. Precision is just the inverse variance, and it's a little easier to work with than working with the variance directly. If you don't believe me, you can try this same exercise with the variance and compare the two. So take a few minutes, pause the video, and see if you can find the right form for the prior and solve for the posterior. So if you look in your table of conjugate priors, recall that I typically use Wikipedia as a reference, you see that the conjugate prior for a Gaussian likelihood is also a Gaussian. So we'll give the Gaussian likelihood a mean of mu and a precision of tau. And we'll give the mean another Gaussian distribution with mean m and precision lambda. We'll let the parameters on the prior be m0 and lambda 0. Typically we would set m0 to 0, but we'll leave it as a variable. So the first step is to multiply the likelihood and the prior to get a proportionality for the posterior. In the next step, I'm dropping some constants and just keeping what's in the exponent, since we don't care about the normalizing constant. Take a second to understand how we got to this, or pause the video so you can follow along on paper. In the next step, I'm collecting all the terms by order of mu. Remember, I don't care about anything that doesn't involve mu because it goes away with the normalizing constant. Take a second to understand how we got to this, or pause the video so you can follow along on paper. The next step is to recognize what form of the equation we are looking for. For the posterior, I want minus 1/2 times lambda times mu minus m squared. Now if you look closely, this is the exact same form that we just found. So the next step is to equate the two by the degree in mu. In other words, the square term goes with the square term and the linear term goes with the linear term. Note that the precision term is simpler to solve, but the m term needs to be solved after because it depends on lambda. And now we have our solution for the new m and the new lambda based on the prior parameters and the data we collected. Take a second to understand how we got to this, or pause the video so you can follow along on paper. So one interesting fact about this is if you look at the precision, this is the precision for mu, and it increases linearly with n. So when n goes to infinity, the precision also goes to infinity. Next, if you look at the second term on both sides of m, you'll notice that the numerator depends on the sum of xn, and the denominator depends on n. So you can see that in the limit, when n is large, this is going to converge to the sample mean of x, which, as we know, in the limit is equal to mu. Last thing to mention here is that if you remember at the beginning of this lecture, I made the point that the Gaussian is a little harder to work with because it has two parameters, mean and variance, both of which can have a prior. So as an exercise to do on your own, if you're comfortable with the material in this lecture, I would recommend trying to solve with the posterior when you have a prior on both the mean and variance. And of course we can extend that further. We only looked at the univariate Gaussian in this lecture, so the next logical step would be to attempt to place a prior on only the mean, but in multiple dimensions. And finally, if you got that, then take it to the final step, where you place a prior on both the vector mean and the matrix covariance of the multivariate Gaussian and solve with the posterior. You may want to try these with the precision first, since the equations are easier to manipulate in that form, and then once you can solve those, try the variance and the covariance. These should take you a significant amount of time if you're doing it for the first time, so take your time and be careful at each step.